my name is Karine Bruyère. I work in the LPMC in French, Biomechanics and Impact Mechanics Laboratory in Lyon. In fact, the session is entitled Elastography, but I gave a title more in relation with the presentation of the work we performed in the lab using digital image correlation. In fact, we use optical digital image correlation in the field of biomechanics for the mechanical characterization of biological tissue, not only elastic behavior, but general mechanical behavior, very often non-linear elastic behavior of biological tissue. We are interested by the behavior of these tissues up to failure and at various strain rates. For application in the field, for example, of injury risk prediction, occurring during a car crashes, for example, here frontal impact with a seat belt. And this knowledge on the mechanical characterization of biological tissue serve as input data for the FE modeling. And by analyzing the variability of these properties due to age or pathologies, we wish to develop a personalized models representative of a quite large population. And of course, for injury risk prediction, we are specifically interested in damage and failure criteria. We realize a lot of in vitro characterization as we are interested in failure of tissues, and it's not so easy to perform conventional tests of biological tissue samples because it's difficult to obtain conventional geometry. Biological tissue are not so easy to cut and to prepare, and conventional boundary conditions also are difficult to obtain. The mechanical behavior of biological tissue presents some heterogeneity, anisotropy. We are interested in large strain, specifically for soft tissue. And as we are interested in different strain rates, we perform dynamic tests. And in these conditions, due to all these constraints, we need to measure displacement and strain field. And we are particularly interested in the definition, quantification of strain-based failure criteria. I have got two slides to recall some principle of the optical DIC, but I will be very short because I'm not a theoretical specialist of the technique. I'm a user. But the idea is to have on the surface of our tissues a speckled pattern. And we use a software, which is DeepPD, from correlated solutions to perform image correlation. Basic parameters of the correlations will help to have displacement field, and after we compute strain field. It's based on comparison of a subset of the speckled pattern with an interpolation of the gray level distribution, and we obtain the strain field, the displacement field, and the strain field. Of course, the results of the computation will depend on the subset size, for example, or the number of steps we analyze. The speckled pattern analysis is used for 2D correlation, so we explore a plane surface, but we also use stereo vision to analyze 3D surface, and for that we use the principle of stereo vision. With calibration, we go the coordinate of a 3D point from the 2D coordinate of this point on the two cameras we use. And you can see here a calibration object that we usually use for the use of the soft big 3D. The most difficult in this experimental works is to obtain a nice speckle pattern, a nice black dot random pattern. He must have some specific properties, non-periodic, isotropic, with a good contrast, etc. And of course, this speckle pattern must follow the strain of the tissue. It may be difficult in case of a large strain, and if we perform the test on the specific environment, for example, in water. So the usual technique is very simple for us. We use spray pens in different configurations. For example, you have an illustration here where we use only the smallest drops of paint to have a very small dot pattern. We can use airbrush, and for tests in water, some colleagues use a special ink. For example, the Bombay India ink is used by a colleague from Marseille, Valérie de Plano, on aorta tissue samples. And to have a very good quality of image, the camera settings, of course, is very important. For stereo correlation, we use two cameras. Of course, the setup of these two cameras must be very rigid. As we use data from the calibration, we must have very rigid camera position. We have to adjust the optical center of camera so that they look at the same point on the surface. Of course, we have to adjust the field dimensions according to the object we have to observe and the calibration of the object. And the most important is to have a good sharpness of the image, and for that it may be quite a lot of work to define the good apertures with the light we can use, and to have a good depth of field. As in 3D, we want to observe some out of plane displacement, and the focus must be kept during this out of plane displacement. It may be quite obvious, but it's very important in case of dynamic tests too, to have a very good synchronization between the two cameras. And for example, we take care to have the same length of cables between the two cameras, and a good trigger the camera for the recording using a normalized signal. So I will illustrate some studies we performed at the lab using DIC, 3D stereo DIC and 2D DIC. First on the skin, and after on the hepatic capsule, and we'll see also something on cortical zone. On the skin, we are interested in the tensile failure characteristic of this tissue. In fact, we are interested in fibrous connective membranes in general, because they present some structural anisotropy, and we would like to develop a structural-based model of behavior and to assess some failure criteria. On skin, we perform conventional tensile tests at various strength rates, and we perform the stereo correlations. So you have here the equipment and the different settings we use for such tests. At the bottom of the slide, you've got a view of a conventional tensile sample of skin with a random dot pattern. The field is about 50 millimeter by 50 millimeter. And the speed of the frame rate of the image recording is 50 frames per second for static test and 5,000 for dynamic test. Here are some illustrations of the video and the image, the strain field from image correlation for static test. So you have at the bottom of the video the strain rate, and for the dynamic tests. And in fact, we have illustrated here a virtual strain gauge, And due to the eye shape of the sample, to sliding at the extremity of the sample, it's very important for us to have a local measurement of the strain, displacement and strain. And you've got the comparison of the displacement, the stretch of the samples using in red the sensor of the machine, displacement from the machine, and in blue the displacement we measure directly with the DIC. And it may be, depending on the geometry of the samples and the speed, the velocity of the loading, we can have a very large difference. Another information useful for us from the DIC is to assess the real strain rate applied to the samples. Here on the left, you've got the nominal stress from the load sensor. You can see a peak at the end of the curve, and we have difficulties to explain this behavior. We thought that the strain rate, in fact the speed of flowing, was 2 meters per second on our samples. And in fact, if we measure directly the strain rate on the samples, we can see on the right, in blue, that this strain rate is varying between 4 and less than 1 meter per second during our test. And it's increasing at the end to 3 meters per second. And this increasing in the strain rate was explaining the peak we had on the forces. And this was due to a system of sliding grips for dynamic testing. And with the DIC, we detected that, and we observed that it was very important to measure directly the strain rate of the sample. As main result of this pencil test on skin, we have behavior curves, stretch ratio curves for the skin, for different strain rates, and we can observe that the strain as failure criteria can be a good candidate for FE simulation, as it's quite homogeneous depending for different strain rates. So it's a recall of all the advantages for us of direct measurement of strain field on the skin for tensile tests. Because we've got eye-shaped sample, we need the virtual gauges. It avoids the bias due to sliding, and for dynamic test, it helps us in measuring the direct strain rate. Specific issues to keep in mind with tensile test is that we have few information in the width of the samples, and that for dynamic test, the synchronization between the two cameras and between the DIC and the conventional measurement is very important. On the liver capsule, the context and the objective of the study is quite close to the one on the skin. We are interested in fibrous connective membranes, and this liver capsule is a membrane made of fibers of collagen and elastin, as you can see on the right at the bottom. We performed some pencil tests on the liver capsule. But to have more realistic loading of this tissue, specifically during injuries by laceration of the liver, when the pressure in the liver is pointing to a rupture of the capsule, we perform biaxial loading by inflation test. So we take off the capsule from the liver, as it's illustrated here, and the boundary condition of inflation test can be circular or elliptical, to have various strain invariants in the two different directions. Here you've got the illustration of elliptical samples with its black dot patterns, and the two cameras used for the stereo correlation. So here the sample is fixed. We have fixation with a ring, a circular one. So here you can see some results in terms of strain field for example, an elliptical sample, and you can see the propagation of the crack at the end of the test. And the DIC allows us to have the strain field and to assess some local ultimate strain near the crack. Here it's quite slow, but we can see the evolution during the inflation of the membranes of the first principal strain of the strain field. And it's not axisymmetric as it should be because of the boundary condition of fixing, which are not very well done. And in fact, we also use such data in terms of displacement this time to simulate the real test by finite elements. Here you've got the model of the capsule with a specific behavioral model for the capsule. And instead of modeling all the capsule and making hypotheses on the boundary conditions, we take as boundary conditions the displacement we measured on this part of the capsules. So it helps to better simulate our test and to validate the behavioral model of the tissues.
How do you apply the stress here in this case?
We've got the pressure.
In the center?
Yes,
okay.
Inside. We've got the pressure, and to avoid the problem of the boundary conditions, we prefer applying this displacement. So here are some illustration of data from tensile test on the capsule. But the problem is that we've got in vitro data from samples. And the question here, we've got a load strain, stress strain curves. Ultimate strain is somewhere here. But the question is, in vivo, or in situ at least, what is the strain state of the capsule, of the liver capsule? So for that we started some experiments on isolated organs, isolated liver first, and we measure the strain field on the main lobe of the liver here. And the question is what to take as the strain-free situation. So the idea is to make the hypothesis that as sample, the capsule is completely free and not stressed or strained. And we observe the black dot patterns on the liver before on the liver under different pressures, and after that we cut the samples. And if we backward the video, gives something like that. We start with the samples, which is cut at the end in reality. This is the first one. And considering the sample is the free strain situation, we compute the pre-strain of the capsule on the liver. It's the same for the second principal strain. Here, the same is illustrated, so we consider the isolated samples as a free strain situation, and we compute for different level of pressurization of the liver the strain state. So the idea is to know where the strain in vivo and in situ, where the capsule strain is comparing to test on samples. Now, an illustration on cortical bone. We started with skin with a quite large field of 50 millimeters by 50 millimeters. On the inflation test on the liver capsule, we are about 30 millimeters by 30 millimeters. Here we study cortical bone, and we have a field of view of about several millimeters. The context of this study on cortical bone is the failure risk prediction in case of falls, specifically with the bone quality and osteoporosis. It's a test I represent for the assessment of tenacity of the cortical bone. It's a bending test on very small samples where a notch of 1 millimeter is realized. So the field is quite small, and some static tests are performed, and also dynamic tests with a frame rate of 6,000 Hz. Here the video of the static strain, and the strain field we measured during this test, and the data we use at this stage are the strain rate. To study the effect of strain rate on the tenacity of cortical bone, it's important to have a direct measurement of this strain rate. And for dynamic test, you can see the image is darker, because of course we have to have more light, and with the same animation on the strain field. And the assessment of the strain rate for the two configurations is quasi-static test and dynamic test. After that, to make the transition with elastography, I will present two slides on a work performed in another labs at the LAMCOS and Lab 2 by Aline Belbruno and Stéphane Kathleen during a work of a student. The context is the mechanical characterization of the cornea in vivo, and here are some preliminary tests on a gel. And Stéphane, do not hesitate to correct if something is wrong. So the method is, the idea is to propagate a shear wave on a gel surface, and to perform both ultrasound elastography and optical elastography by first 2D DIC. So the shear wave propagation for optical elastography has been recorded by phantom camera at 4,000 Hz. And on the right you have some examples of the displacement field obtained from both ultrasound images and optical images. So the two cannot compare directly, but the idea is to show that with DIC, optical DIC, the shear wave propagation is well seen, and it's possible to assess the velocity of this shear wave, and the preliminary results are quite close between the two techniques. So it's a promising study for cornea characterization. Thank you for your attention.
We have time for a couple of questions.
I have a question about the first application. What are the parameters of a good random pattern?
For a better correlation, the size of the dot pattern is important compared to the resolution of the camera and the field you observe.
It's small.
Yes,
small.
we need very small. We need smaller, for example, on the cortical bone, because the field is very, very small. With paint spray, we were able to perform quite large dots, and also very small for very small size of field, like for the cortical bone. And for that, we use the smallest drop of the paintbrush, and for that we threw away the biggest with ventilator in French, with a hair.
And you don't have any quantitative parameter, just like autocorrelation of the pattern or something like that? No?
Yes, we have. I don't have them in mind, but we have all this information. So we optimize this, but in fact we have. It's difficult to. We perform some tests to see if the correlation is to optimize the correlations and to see if the size of the dots is okay. We try to have several pixels in one dot, and we need to have several dots in one subset. But the size of subset is filtering the strain field we obtain, so it depends on the resolution we want on the strain field.
Yeah. Last question.
Just a comment on the last slide. In this experiment, we did not put any dots. It was the natural texture of this phantom that was used for the tracking.
Okay, so last question.
Okay, so also on this slide, actually, you're looking at cornea. Have you also looked into or comment on what is the difference between, let's say, your method and, for example, a similar measurement using optical coherence tomography?
Using optical?
Optical coherence tomography, OCT.
I don't know. I don't know this technique.
Okay.
Here we are only with surface, as OCT can go in depth.
Computed tomography. Oh,
no.
Optical
coherent tomography.
coherent tomography.
Yeah. You can. Yeah.
Yes. Here we have only a surface observation, an optical observation of the surface. I don't know. I've never seen the use of these techniques. But for example, on bone, real 3D correlation images from CT scan can be used.
Yeah, the reason I'm asking is that, I mean, for bone, I completely follow what you're saying. But for the eye, OCT has been a clinical standard for many years.
I don't know I haven't not done the literature review on this, but maybe some use the OCT to perform correlation.
So really the last question.
It's about the speckle. So you show the speckle image of the gel surface, as I understand. And in the case of you will work with the cornea, it's a completely transparent medium. So how will you get speckle from the cornea?
It's preliminary test on a gel, so it already has a texture of the image. On the cornea, in vivo, I'm not sure. Stefan, is there a texture of the? No.
Probably not.
For application in vivo, the idea is to have a natural texture because it's difficult to have to put a specific speckle, external speckle on the surface.
I propose we thank the speaker.
It's more in terms of what is the speckle and what is the optical coherence tomography. Optical coherence tomography is an interferometric technique, and speckle is more the noise analysis. So in such a way, as he's mentioned, the optical coherence technique has much more resolution because the quality is based on the concept. Speckle is a random, and then you have a much more wide points of analysis of the surface. But in terms of the quality of the surface, it is the optical coherence tomography.
But OCT is also measuring speckle, so.
Yeah, correct. But but it's a complementary. it's a complement. The OCT is in the front. It's in the front, so it's much more resolution.
And also speckle interference.
Well, it's random.
So, okay, I propose we continue this after. I propose to thanks all.